There we go. Alrighty then. Let us begin. I got to go down to the right portion because we're starting with cache memory problems. Can I annotate? Where's my draw? There it is. All right, cool. So to start, we're going to start with this problem, which is this is just standard. This is standard cache memory stuff. So similar to the clicker questions, essentially you're just going to be given the word problem and the conditions, and you'll have to calculate all the different stuff like the byte offset, block offset, index, total address, and well, tag from the total address after subtracting off the rest, so on and henceforth. So this one is more similar to the stuff we did all the way at the beginning when we were introduced to the topic, where we're given an initial amount of memory. So the way she does stuff in class is a good way to start when you're given big chunks of memory like this, which is reduce it to a power of 2. Oh wait, no, this is useless. 4 GB main memory has nothing to do with this. We're looking at the cache. So this is 64 megabyte cache. So you want to reduce everything to power 2, or you can leave in megabytes, however you wish. So in this instance, you want to pick out the important data. So first thing you want to pick out is the size of the cache, which is 64 megabytes here. Size of a block is comprised of 16 words. Size of a word is comprised of 32 bits. You could also write that 32 bits is 4 bytes if you wanted, which it's up to you. And then it tells you to show the fields of memory address if the cache is a 4-way set associative. So this tells you that there are 4 blocks per set. So it's one set is equal to 4 blocks. So when you get given information about an n-way set associative, with n being any positive integer, the rule is that any n-way set associative system is going to be 1 over n blocks. So that's the one very important rule to remember about set associative, because full associative is obvious because you immediately know that however many blocks there are in one set. And then with direct mapped, you always know that you have 1 block per set. So this one varies a lot because you're going to have to do math to figure out, how many sets you have and how many blocks you have. Well, no, it tells you how many blocks you have per set. You're going to have to figure out how many sets you have using this information. So it says you have to show the memory fields. What that means is that stuff she does in the clicker questions where she draws a little rectangle and then, breaks it up into pieces that are not drawn to scale because we're not good at that. And then you're going to have 4 portions. You're going to have your tag at the end. That's an A. Tag at the end. You're going to have your index. You're going to have your block offset, and then you have your byte. So these are the 4 main pieces of information that you need to get from this problem. And you've been given the total size of the cache, the blocks, the amount of words in a block, the size of each word, and then you've been given the amount of blocks in a set. So first thing you need to do is calculate the amount of sets in this 4-way set associative system. So let's think. Actually, you don't even need to do that really, because we don't actually need that, huh? Well, we can calculate the block offset first. So to calculate the block offset only, essentially all that means is how many bits of information do you need to select within a block any given word that you want. So in this instance, can you guys see if I write over here?
Yeah, I can see that.
Okay, good. So I have a lot of space. So whenever we could start with byte or block offset. We'll just start with byte just because. So for byte offset, what this means is it's how to select any given, how many bits do you need to select any given byte within a word? We're given the size of a word. A word is 32 bits, but I also said you could represent it as 4 bytes. This simplifies this because 4 bytes, how many bits do you need to represent 4 states? If you have 1 bit, it's a 1 or 0, that represents 2 states. If you have 2 bits, that can represent 0 to 3 decimal, therefore that can represent 4 total states. That means that our byte offset is just going to be log base 2 of the amount of bytes in a word, which happens to be 4 here. And this is going to be equal to 2, and this unit is bits. So the byte offset is the log base 2 of the amount of bytes, not bits, the amount of bytes in a word, right? So the thing is, I never use this log 2 thing. Like, of course, when stuff gets bigger and such, it's good to know the log 2 stuff, but I prefer to think of this as how many bits do you need to represent the amount of states that you need to be able to select from? You need 2 bits to select from 4 different states. You need 3 bits to select from 8, and so on and so forth. And that rule carries through to the block offset as well. It's basically the same thing. You're given this information. Blocks are 16 words. So how many bits do you need to represent 16 different states? Well, if you need 3 bits to represent 8 states, 4 bits represents 16 different states. Therefore, the block offset is going to be 4 bits. So you don't even really need to use the log if you don't want to. Of course, when numbers get bigger, if you're not really good with your powers of 2, you have a calculator with you, so feel free to use it that way if you'd like. But I prefer not to. I think it's a little bit of a waste of time. So far, we know that, oh yeah, we're going to have to calculate the total size of the cache, aren't we? Our total address. So let's think. Actually, no, we do need to calculate the amount of sets, huh? No, we need to calculate the index, which is the sets. All right, so we've calculated the byte offset, which is 2 bits. We've calculated the block offset, which is 4 bits. So far, we're running tally as 6 bits has been allocated in our, as of now, unknown size address system. It does say the memory system is byte addressable though, which is good to know, because if it were addressable, we wouldn't have a byte offset, which is good to remember. If you're word addressable, that means that's the lowest level. So that's another keyword to remember, because if you're word addressable, that just means that you do not have a byte offset. So you start at the block offset. Because if you're word addressable, that means the word is the lowest level of abstraction in your address. So you can't select within a word. You can only select between them. Even so, the next thing we need to calculate is the index. Now, calculating the index is essentially indistinguishable from calculating the amount of sets, because the index allows us to select between our sets. The index lets us pick which set we want to go into to find data. So the index is no different than calculating the amount of sets. So this one's actually going to take a little bit of doing. So we have to start with the size of the cache, which is 64 megabytes. And then we immediately start multiplying by all these ratios that we have, right? So the first ratio is going to be, we can decide, we did do this, so we can do it this way. So we can first do the word ratio, but instead of using one word is 32 bits, we'll do one word is 4 bytes instead. One word is 4 bytes. It's better to work in bytes because the megabytes is already in bytes, so keeping it in the same unit is easier. After that, we then need to move on to the amount of words in a block. So we have 16 words per block. So we have one block plus 16 words, or over 16 words. And then the last thing we have is this piece of information. Look, I placed it so tactically at the beginning. 1 set over 4 blocks. So there's 4 blocks per set. When you calculate all of this out, you can either do this, you would have a calculator, but you can also do this in powers of 2. So the way you do this in powers of 2 is reduce the fact that 64 megabytes is equal to 2 to the 26th power. And then you would have this, which is 1 over 4 bytes, which technically is 1 over 2 to the 2nd power, or 1 over 4, right? So you could also write this as 2 to the negative 2. Either way. And then so on and so forth. The next thing's going to be, what is this, 16 blocks per word. In order to represent 16 different states, you need 4 bytes. And then in order to represent 4 different states, you need 2 bytes, similar to the byte. So overall, we're going to have 26. So the power of 26 subtracted by the power of 2 from this portion, subtracted by the power of 4 from the block offset, subtracted the power of 2 once more from the sets, the amount of sets per block, or the amount of blocks per set. This leaves us with, 26 minus 8 is going to be 18. That's a horrible 8. 18, which will be 2 to the 18th, which is equal to the amount of sets we have here. So now this is where it's okay to use log base 2 in order to solve the, this is okay to use log base 2 in order to get the amount of index here, because you need to pick between 2 to the 18th sets. So log base 2, where's the calculator? Log base 2 of 18 will give us how many bits we need in order to represent that amount of sets. Where's my augmented log base? Does anyone have a calculator that's faster than me? Let's see. Oh boy. Log base of 2 to the 18th power is 18. Oh, wait, never mind. I'm dumb. I didn't need to do that. This is the amount of bits you need to represent the distinct amount of states because, yeah. Okay, I derped there. So now our running total is 6 bits have been allocated for the byte and block offset plus 18. So far we've allocated, what are we talking, looking at 24 bits? 18 plus 24 is 24 bits total have been allocated in this portion of memory. So what's remaining is the tag. So in order to calculate this, we're going to need to know the total size of an address. So where do we get that again? Let's see. So far we used 24 bits. It doesn't tell us specifically, does it, the memory address? It says byte addressable. Where is 32 bits? Oh, I get it. All right. Remember when I crossed this out and said it wasn't that useful for the cache stuff since we're calculating cache? Well, that's a lie because main memory is still going to matter because we need to be able to address anywhere in main and then fetch it and put it in the cache, right? So total address length is going to come from this. So in order to address to 4 gigabytes of memory, this is just something you can memorize. 4 gigabytes requires 32 bits to address to. So this would be our total address amount. So this is how much address you need in total in order to access any portion in here and move it to the cache and so on and so forth. Therefore, if we have 32 bits of total address, we have 24 bits allocated for the index, the block, and the byte offsets. That allows us to say 32, oh boy, 32 minus 24 gives us 8 bits of tag. So tag has 8 bits. Oh, really squeezing it in there. So this is all you would have to do. Technically, you could just draw this block and write the number 8 in here. You could write the number, what did I say? It was 18 for index. You could write the number, block was 6 bits. Yes. No, block is 4 bits. Block is 4 bits. And byte is 2 bits. And this would probably be fine. So your answer to this question could technically just be this rectangle with the numbers of bits allocated, and you need to indicate which is tag, index, block, and so on with these little words if you'd like. So are there any questions particularly? It's a little confusing because the word problems can change a lot. So are there any questions about like where I got a number or something like that?
I just had a question on, I don't see your writing for it, but I know you talked about it, where the 4-bit came in from, like underneath the log 2 of 4.
This?
Yeah, or like right underneath it, like where you have it like with a square outline. Yeah, that.
Oh, this, I'm kind of thinking I messed up there. I'm pretty sure I said something wrong because, oh wait, never mind. No, I'm wrong. No, that does come from somewhere. So the 4-bit comes from block offset, which is 16 words, right? So up here when I was calculating the byte offset, I explained that if you get the byte offset information from the amount of data or how many bytes you have per word, 32 bits is equal to 4 bytes. Therefore, you have 4 bytes per word. In order to represent 4 distinct states, you need to have at least 2 bits. That's how you do this. That's the same thing as taking log 4 of the amount of bytes. Now you can use the same log trick if you'd like for the amount of words in a block. If you do log base 2 of 16, it spits out 4 bits. But the way I think about it is how many bits does it take to represent 16 distinct states? 2 to the 4th is 16, so 4 bits. So it's this, that's where you get that. So the 4 bits comes from the words in a block.
Okay.
That's the block offset.
All right, that makes sense.
Yeah. And then one thing to go over one more time, because we haven't done it in a while for the clicker questions, because normally in the clicker questions, we're just given the address length, whether it be 16 bits, whether it be 32 bits, so on and so forth, 128 bits. So in this instance, the trick is you have to remember that this under here, it's 4 gigabyte main memory. you need to remember that the total address length of any given system is the amount of states or amount of bits it takes to represent the distinct states in the main memory. So 4 gigabytes is equal to 32 bits. So 32 bits will give you however many bits gigabytes reduces to. 32 bits of address will allow you to select between however many hundreds of thousands of locations are in 4 gigabytes. So you need to use the main memory. So if you reduced gigabytes into its powers of 2, you would probably get, pretty sure it's just going to be 2 to the 32nd. So it's good to remember something like that. But you could also just brute force it by hand if you'd like. So that's how that works. I'm going to, can I just clear that? Pog. All right, nuts. So after that, there's this next question, which while it isn't exactly cache memory, it's appeared a lot and it's similar in type, where it's like a similar type of calculation. So it's good to, you're going to want to know how to do these anyway, since it showed up on a couple of these finals I've reviewed. So I'll go over how to do this as well really quickly. In order to mouse, I have to do this. There we go. Drawing. There we go. All right. So how this works is if you want to build a 2 to the 48 word, 256 bit per word memory, and the only parts you have available are static RAM chips that contain 2 to the 18th 8-bit words each. Part A, how many rows are required? Part B, how many columns are required? Part C, how many chips in all? So the first things first for rows. So we're given information here with this 2 to the 48 word. So word is the base unit for the 2 to the 48 term. So let's get that down. 2 to the 48 words. And then we need to figure out how many, this is for part A, rows are required. And the only parts we have are static RAM chips that contain 2 to the 18 8-bit words each. All right, cool. So we're only given 2 pieces of data here. We're given 2 to the 48 words total. So this is the total memory size we want for the system, but we want the system to also have 256 bits per word memory. And the only parts we have available to us are RAM chips that contain 2 to the 18 8-bit words each per chip. So in order to find how many rows are required for the system of these chips and such, you just do 2 to the 48 divided by 2 to the 18th, which is the other unit of words that we've been given, which is down here. And this is just 2 to the 30th, I believe. Yeah. 2 to the 30th. And then part B, it's asking how many columns are required. So columns, rows correspond to the first unit, which is 2 to the 48 words. And this is also words. Now rows correspond to the second unit that we've been given, which is the bits per word, right? And this is 8 bits. So in this instance, if you want to calculate columns, you then have to do 256 bits divided by 8 bits, which spits out 32. That's a horrible 2, 32. So this means that our rows, we have 2 to the 30 rows, which is an absolute crap ton, and we have 32 columns. Rows, columns. So we have 2 to 30 rows, 32 columns. And the last thing is how many chips in all. So in order to calculate how many chips in all, we just multiply these things together. So 2 to the 30th times 32 is equal to 2 to the 35th. 35th power. Big numbers. So this is what happens. And the total answer for number C, this is the amount of these static RAM chips that you need in order to have this system. So this went over once in one, what was it? It was one lecture where we did a couple clicker questions on problems like this, where she was drawing out the rectangular shaped systems for memory. And we had to calculate stuff based on, you know, how much chips, what like the dimensions of the chips we have and how we're going to orient these things in order to build the system that was specified. So for these things, you'll see that for all of them, similar to this one, it doesn't have much information to you available to you. So you just need to memorize or remember which one is columns and which one is rows. So columns tend to be the larger portion or the larger unit. So a word is a larger unit than bits per word. And that follows for both. So you just have to remember the order of operations in these instances. Are there any questions on this one? It's kind of hard to talk about these since probably nobody even remembers that we did them because we did it once and never looked at it again. But I could try to do my best to help understand or help you understand if you have questions as to how this is done.
I understand that one pretty well.
Yeah, so
I don't
it's
know if anybody
just
else has questions.
yeah, it's just like the trick. I'll give a trick for these questions actually. So the trick for these questions when it's given to you is there's two unit types. Now it doesn't necessarily have to be a word, but if you're given, let's say, word and then something next says bits per word or something like that, or 8-bit words, you can tell that the 2 to the 48 corresponding to word means the word is the larger unit because 256 per word, this is telling you how much is within this unit. So in order to calculate your rows, you work with this number first. And everyone knows how to do division. You do first divided by next in order to find the rows. And then the next step that you want to do to calculate columns is bits per word, which is your secondary unit here. 8 bits here, 256 divide. And then since these are, as you may or may not remember from the lecture, rectangular or theoretically square systems where they have dimensions of length and width, you just multiply those two dimensions together and you will get the how many chips in all, which is the last piece of information you need. So for these ones, there's a reason it's only really 6 points. Technically, it can be done extraordinarily quickly. So let's move on. Give me my mouse back. So this is nothing that we're focused on right now. This is just writing programs. This is the stack. Fun. Stack time. Oh boy. All right. This is going to take some time. I think we have a bunch of, yeah, nuts. All right. Well, let's look at it. So first things first with stack is you always want to trace the program. Sometimes she tells us which instructions affect the stack, and sometimes she doesn't tell us which instructions affect the stack. So in this instance, we start by marking all the instructions that affect the stack. So the rule for stack tracing on exams is every single time an instruction affects the stack, when you find an instruction that modifies or affects the stack in any way, oh, I gotta go back to my mouse, it gets its own box. Regardless of how insignificant the instruction may seem, it could literally change nothing about the stack. You still have to give the instruction its own box. Hence the reason she gives us so many boxes. Now, when it comes to the final, it completely depends on the program she gives us and whether or not it'll be a less complex or more complex stack tracing problem. In this instance, you can see we have quite a lot of boxes, but in some other finals, we don't have that many boxes. So it's really just luck of the draw when it comes to these things. So we'll start by marking instructions that affect the stack. So the first things first, we immediately start with move SP, #0 or #0, however you'd like to say it. This counts because we are affecting the stack pointer. This affects the stack. Next line, sub SP SP4. This affects the stack pointer. That counts. Next line is add FP SP0, frame pointer and stack pointer. That affects the stack. This counts. Move SR1 to 1. This does nothing to the stack. We can leave it alone. Move SR05. This does nothing to the stack. We can leave it alone. You're going to need another thing about these stack tracing problems is you're also going to need to be pretty decent at just general program tracing, which is still a little annoying for some people. But in this instance, I hope everyone recognizes what happens next here. We do a branch link to power. So we go down to power and we immediately start here with a push FP. Now push FP affects the frame pointer. That means it affects the stack. We're going to need to focus on this one. Next line is sub SP SP20. That affects the stack. We're going to need to focus on this. Then we do add FP SP0. That affects the stack. We're going to need to focus on that as well. This one is store R0 into the location of FP4. Now, this one's a little tricky. Does this or does this not affect the stack? So technically, since this is a store instruction, it doesn't have to affect the stack, but it has the ability to affect the stack because store just shoves whatever register is its first, condition. It'll shove whatever's in that register into the memory location specified by the next condition. In this instance, that memory location happens to be the frame pointer, which happens to be within the stack. Therefore, this instruction does affect the stack, and so does the next one. This will also affect the stack. Moving on. Wait, no. Move S is 60. All right. Another store, move S R3 to 1 does nothing to the stack. We don't have to worry about it. This down here, store R3 FP12, that is also something that affects the stack, line 64. Yep, oh boy. Let's move down. And we have a branch L4. So we immediately jump to where L4 is in this code, which is down here. We are load register, LDRs, load register with the frame pointer. So this, as far as I'm aware, does not affect the stack. Even though it has the frame pointer as part of it, this is a load command here. So what this is doing is taking whatever is specified at the memory location, in this instance it's at the frame pointer, and is loading it into R3. Now, it's not moving it from the frame pointer into R3, it's taking a copy and putting it into R3. Therefore, this doesn't actually affect the stack, so you can leave it alone. So, oh wait, I missed one. Wait a second. This said branch L4. Jump here. Okay, well, we branched L4 and we did that. So now we got to keep moving on. Compare does nothing to the stack. Branch greater than L5 does nothing to the stack. Load register. This is yet again takes a copy, so it does nothing to the stack. Move R0, R3 to R0. This does not affect the stack. Add S, FP, FP20. This does affect the stack because it's operating on the frame pointer, so it'll move the frame pointer. Move FP to SP. This part right here is something to remember because when you do this whole move SP FP portion, this collapses the stack. This means when we do this, it essentially means we're done using the stack. When you do this in actual code. Then down next, we have load register FP SP4. So this also affects the stack because you're loading the contents of the stack pointer onto the frame pointer. And I think this means SP with the 4 means you add 4 to this, if I'm not mistaken. And then it shoves it into the frame pointer. So this is important as well. So that is all the code, right? I believe so. Not quite, actually. So we went down through this and we were branch linking and stuff and jumping around. But for the purpose of stack tracing, sometimes it's best to run through and skip branches and just keep moving through just for the sake of finding all the instructions. So if we were to skip this, if we store R0 to frame pointer, that affects the stack. If we add S, FP, FP, that affects the frame pointer, that's part of the stack. Move SP, FP, this is another collapse the stack thing, so this counts as well. Jump through. We already did push FP counts, branch B to be done counts. Line 60 doesn't count. I think beyond that we've touched on. This is a load, so that does nothing. Load does nothing. Mul doesn't affect anything. Store, this counts. Line 84 counts. Load doesn't do anything. Sub S doesn't do anything. Store into the frame pointer, this counts. Load doesn't do anything, and beyond that we hit everything. So first step, does anyone have any reasons to dispute any of these or want to ask questions as to why I highlighted certain lines and as to why I picked those for the stack tracing? Are there any disputes? If not, we can continue on with some examples.
I don't have a dispute, but just one thing that I've had a question on. Where does the BXLR like branch to next?
The one at the end?
Yeah.
All right, so BXLR is in response to this line, which would be line 20, BL power. So when you do a branch link, that's different than just a regular branch. So branch link will store the next line's program counter designation. So in this instance, the branch link power at line 20 would store in memory 24. So line 24, it would store the next 4 bytes. So functionally it's doing PC equals PC plus 4 and storing that somewhere for later. You do all your code after you do the branch link, blah, 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 blah. You get down to the bottom. BXLR. The LR is known as the link register. What do you think we stored in the link register? we stored that program counter information. We stored line 24's address into the link register. That's what the branch link does. So what that means, when you approach a BXLR, you need to find where the branch link that preceded it occurred. There are no other branch links in this entire program. Therefore, the only place that this BXLR will send you to, it'll go from line 32 and send you all the way back to line 24. And then you execute and continue running down the program from there.
Okay.
So that's what that does. So
Thank you.
that's more of a function thing. While it can help with the stack, branch linking and BXLR and stuff like that is primarily used for functions. So in this instance, power is a function technically, since we're using BXLR. It's just a function that has other loops, the L5 and the L4 loop in it. All right, so that's that. So let's count the amount of boxes we're going to have to use here. So we have 1, 2, 3, 4, 5. We have 6. We have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. We have 17 boxes total, it looks like, unless I'm counting like a numbskull. So that means we would have to fill, moves, 17 of these boxes. So luckily we start with 12 boxes. We're given, lucky us, we're given 18 boxes, which that's almost just enough to cover what we need, which is excellent. So this is a little difficult because I don't want to get rid of the nominations for, don't want to get rid of these. All right, oh well, we're just carrying down. So I'm probably not going to go through every single one of these instructions. I won't do the entire problem, since I still advise that you guys go back later, like before the exam, which I think is what, Thursday? Yeah. Before the exam, and go over the solutions to these yourselves, or take the test yourselves and then compare the solutions, because the only way to get better at stack tracing is to just do a bunch of stack tracing problems and just get used to how to fill these charts in. So I can go over the effect of some of these instructions. So actually, it's probably better if I open up the solution and show that instead, so I don't have to get rid of these. So give me a second. I'll open the solution in another window. All right, I got it. Scroll down. There we go. All right. This came in. Oh, that's funny. All right. Here's the solution for this. So, so we know that the first line affects the stack. It's the move SP0. Move SP0, remember you got to record the instruction as well, literally does nothing to the stack. Doesn't select any of these addresses. It just does straight up nothing. All it does is say that the stack pointer's address is now 0. It fills the stack pointer with 0. Now what happens when you do the next instruction, which is sub SP SP4, which means subtract 4 from the stack pointer? Well, what happens when you're at the address location 0, as in the first address in existence in your computer, and you subtract 4 from it? You don't go to address location -0. Computers loop all the way back around to their highest address when you do that. And in this case, the highest address in this system that we are aware of is FFFFFFC. So that means the stack pointer is now, as you can see by the blue highlight in the second box, at that location. But that's all that does. It simply moves the stack pointer to a new address. So it goes from address location 0 all the way up to the highest address in the system that we have been made aware of. So the next instruction, which is add FP SP0, essentially means add 0 to SP, which does nothing, and then SP is stored into FP. So you take a copy of it. So this green highlight in this instance designates when both the stack pointer and the frame pointer are at the same memory address, because you'll see later on in the next box that the green goes away and you get a blue and a yellow, with blue representing the stack pointer and yellow representing the frame pointer. Now on the exam, I do recommend, since most of us will be required to take it in person, I do recommend bringing, a marker, like 3 colored markers or highlighters, because it actually really simplifies this. You could just use a pencil and draw a little arrow next to the box pointing to any particular address and write FP, SP, that kind of thing. But if you just have the ability to just highlight over it and put, in the upper right-hand corner, a little legend that says FP equals this color, so on and so forth, that saves you a lot of time. So I recommend doing that, even though we're given 2.5 hours for this exam, right? Far longer than normal. This exam's still out of 100 points, which means in theory, we're given a lot more time than we should need. If I had to take a wild guess as to how long these exams should take for someone who's, done a little bit of studying and some practice on them, you could definitely finish these exams in the standard exam time. She could give this exam in our standard, hour and a half period, and it could be reasonably assumed that you'd finish it. It's not that bad time-wise, but it's possible to get tripped up on certain things like the stack. So we'll move on past that. So what happened here was now the frame pointer and stack pointer are in the same location, but yet nothing has affected the stack in form of values. Now, the ways that we know to affect the stack value-wise is to either use a push command or a store command. So the next line just so happens to be a push command, and it's pushing the frame pointer. Now, you got to remember, what did we do here? We put the stack pointer, which remember holds this value, 7FC. We put it into the frame pointer. So when you push the frame pointer, remember the rules of push means you increment the frame pointer by 4 beforehand. So you pre-increment it, meaning you increase, well, decrement in this case, you're decrementing it. So you take 4 away, which moves the frame pointer up 1 block position to 7F8, and then you input the data held within the frame pointer into the value slot. Hence the reason you see the stack pointer is now held within the frame pointer as a value, and the frame pointer has moved. So a very important rule to remember is when you do pushes, you technically decrement, because remember, we're working with the highest value at the bottom, lower values at top. So you technically decrement the stack value or the memory value of the frame pointer by 4, which moves you down from C, which is technically decimal 12, to 8. And then you input the data. When you do a pop, you're taking a copy. Pop does not remove data, it takes a copy. Pop very much acts like a load register command in that respect. But in that case, you increment, as in you add 4. And that is done afterwards. So you increment it afterwards. So pop, you move it before, then put the data in. And for push, you move it before, put the data in. For pop, you take the data out and then move it. And the reason that's set up is so you don't just like lose data or accidentally miss something. Because if you were to do decrement or increment on the same order as in first before you operate on the data, you're going to miss data. You're just going to have blind spots, and that's no good. So that's like something very important to remember is how the push and pop and load register commands operate here. I mean, store commands operate on the stack. So next thing that we do is we do sub SP with the value of 20. So 20 divided by 4 is 5. So all that means is you move the stack pointer up 5 values, right? 5 boxes. Technically I should be saying down since we're going to lower values, but from our reference and how we're doing this, it's moving it up. So in this instance, you just need to know how many times this is 4, because this is yet again byte addressable, the favorite thing and favorite word of the class. So we move this up. So currently it used to be at this position, move it up 1, 2, 3, 4, 5. Now we're at the highest address we have in the system, which is 6FE4. And that's all that did. It didn't operate on any values. All it did was move the pointer. And you'll find that a lot of instructions tend to do nothing but move the pointer, which is why the highlighters are so useful, because it lets you really just grind through them very, very quickly. So next step, you'll see that add FP SP0. All this is doing yet again, whenever you see this add FP and then SP0, all this is really doing is moving the frame pointer to the exact same position that the stack pointer is currently at. Hence the reason you see it go from here to the exact same position where we get our beautiful little green color again. So moving down to the next one, we have store R0 FP4. So here's the thing, FP comma 4 within brackets is addition. So that means you take the value of the frame pointer, which is currently E4, I'll just leave the F's unspoken, and add 4 to it, which means E8. So this means technically, we're not actually changing the value of the frame pointer, we're changing the value of memory where this store is going to occur. So the frame pointer doesn't move, but the frame pointer doesn't move, but technically the data that's being put in is 1 position higher because you added 4 to the frame pointer's value and then shoved the data that was held within R0 into this location. So this is where you can see stores act very much like pushes technically. In fact, this isn't actually a push because you can see it moved it down one, because a traditional push moves it up one. But it acts very similar in the fact that the store will put data in wherever it's told to, similar to the push. Now the next line here is store R1 simply at the frame pointer with no extra operation. So this acts how you'd expect it. Wherever the frame pointer currently is, it just shoves that, whatever's held within R1, just shoves it in here. Just so happens it has the decimal value of 1, which, another thing, stack tracing and program tracing are one and the same. You're going to need to know what the program's actually doing, as well as how it's affecting the stack at any given time in order to properly solve these questions. So it's important to keep track of register values. On past exams that we've reviewed in the past, she had like a register box to trace values of registers, but that's really just program tracing. So she's kind of foregone that for most exams, but I still recommend that you draw your own chart somewhere, have an extra piece of paper to keep track of the register values, because you need them, because they end up affecting the stack. So we were up to line 56. Next, we do store R3 into frame pointer 12. So this is adding 12 to the frame pointer. Frame pointer's current location, adding 12. This technically just means move 3 because 12 divided by 4 means 3 positions. So you go 1, 2, 3, which means technically we would be storing whatever R3 is in here. But she has an error in her solution here because she didn't put the 5 in here, but it shows up over here. But you can see that you move up 3 spaces and then you shove 5 into the position. So she just forgot to put the 5 here. Even so. No. If you did this store command twice, it's a little tricky. Oh wow, something went wrong here. Either way. Next position is store R3 at the frame pointer, line 96, which just overwrites what was currently there. It just puts a 0 in instead of a 1 because during the program's execution, the value of R3 changed. And so on and so forth, moving around the stack pointer and stuff. And it's really, you can see that 17 boxes of this sounds like it takes a while and sounds difficult, but in reality, we went through, we picked every single command that affects the stack, and we were able to fill these out in a little under 20 minutes if you were really speed chunking it. So these don't actually take that much time once you've practiced and you understand what's happening. And these commands are just finishing it up, Let's look at what the move stuff does. So you'll see that you have green, 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 and then we have store R0 frame pointer that just puts something in there. Then we do this add s fp fp4. So this is fp equals 0. So all this is doing, oh yeah, here, allow me to explain. This is a tricky one. So in the previous example, or previous block, we have 7fc, which means both the stack pointer and the frame pointer are at this position, which is the highest position in memory. What happens here, add s fp fp4, is you added 4 to fp. So what does that do? Well, this is just doing the opposite of what we did all the way up here with this 0 and then sub to move the stack pointer from the address 0 all the way to the highest address in the system. This is moving the stack pointer from the highest address in the system to address 0, which is why it says fp equals 0 here, which is why we lost our green and now we're stuck with just the stack pointer. And then the last thing we do is move FP or move SP FP, which means take this frame pointer's value and put it into SP. We know frame pointer is 0, therefore the SP has just been reduced to 0. So this is collapsing the stack. We're no longer using it. We don't need to keep a frame pointer to allocate a portion of the stack for us to use during the duration of our program. We can say we're done. And that's exactly what happened. And then you're simply left with the values in the stack because you never pop stuff. You never take stuff out of the stack, you only overwrite it, which is actually a security threat, but either way, that's what it is. So are there any clarifications or questions that people would like to ask about how to operate on the stack and like do's and don'ts for certain things? Like rules and such? If not, we can move on to other examples because this is this entire final. For the purposes of today's review, we're only going over stack, pipelining, and cache. So this one didn't have any pipelining to my knowledge. Yeah, no pipelining. All right, cool. I'm going to clear all the drawings. All right, let's move. So this was a solution, so I'm gonna get that out of here. We don't need this. We did this final already. So which one was this? We just did this one. Let me check. No, this is a different one. This is the, oh boy. This is the December 14th, 2018 exam, which is the fall 2018 exam. So let's scroll down to, that's all that. Yeah, so you'll see that just like this one actually has pipelining though, which is good. But you'll see that just like the last exam, you have a 10-point problem that tells you this is a cache problem. And this one happens to be two-way set associative, and it tells you it's byte addressable. And then this next thing that I said previous, you're going to have to do every single time that weird square memory system. And you're given RAM chips and you have to find the dimensions of the system memory-wise, right? So these things are 6 points, these things are 10 points. And then right here, you're given a pipeline problem that is 6 points, which is nice. Cool. So does anyone want to go over another example of this cache problem or another example of this, or do you want to go right to the pipelining since we haven't done one of those yet?
Can you go over number 11, please?
You want to do, okay, I got you.
Yeah, thank you.
All right, let's get it. Got to turn on my drawing then. Let's get that. All right, let's first pull out the information that's important out of these little word problems. First things first, 32 gigabytes main memory. When you're given this information, you immediately know that you need to figure out how many bits of address you have. Now, let's think. 4 gigabytes main memory means that we have 32 bits of address needed in order to reach any given address location within that 4 gigabytes. So you need 32 bits. Well, 4 gigabytes takes 32 bits. 32 gigabytes takes how many bits? That kind of feels like it takes, actually no, this is powers of 2. So let's just do this the easy way, which is log 2 of 32. Well, here's the thing. 32 isn't the number, obviously, because that's not going to work quite right. So you need to do log 2 of 32 gigabytes. So in powers of 2, a gigabyte's represented as what is it? It's not 2 to the 18th, is it? What's the rule? How many numbers is this? Let's get out the calculator. That's a big number, ain't it? Yeah, it's a little wild. But what if we do this? That's not enough, huh? Okay. So using the calculator, this works out to be 35 bits of address, which is really weird because it's not a power of 2 address. So let's go over the rules on gigabytes. So let's go over the representation of gigabytes powers of 2, because that seems like it's very important. Gigabyte and powers of 2. Let me look at this real quick. Powers of 2. Ba, ba, ba. All right. Ba, 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 ba. Choose them in 9 bytes. That's wild. All right. So this is gigabyte. This happens to be equal to 35 bits. I'm going to look into this and try and get that for later. But for now, this is the address size. So I just need to know the exact power of 2 that a gigabyte means, because we have 32 and that's given, but we actually need the power of 2 that gigabyte represents. Does anyone remember that off the top of their head? Let's think. Is it 2 to the 9th or 2 to the 18th?
Somebody said 2 to the 30 in the chat.
I feel like that's too big.
Okay. Yeah.
But yeah, he did say that, but let's see. I'm reading
I calculated
something
it to be 20.
to the 20th.
Yeah, log of 1024 times 1024 divide, or log base 2 of 1024 times 1024.
So
Did I forget an order of magnitude there? I think I might have.
it's weird.
Wait,
We're
I
operating.
forgot an order of magnitude.
So what is it? What does it work out to be? Is it like 20 or something?
30, like the person in chat said then.
2 to 30? Well, we can test that, can't we? So if we do, let's see, math, we're going to work to the log base function, log base 2 of 32 times 10 to the 30th. No, it's 2 to the 30th, huh? Let's see, 32 times 2 to the 30th power. Huh. Eric's the winner of the day because he is correct. Gigabyte is represented by 2 to the 30th. So in powers of 2, the gigabyte symbol is 2 to the 30th. So for this, we do 32 times 2 to the 30th. It looks like 230, huh? Let's well, hopefully I'll just remember. So log 2 of 32 times 2 to the 30th is equal to 35 bits. So this is the total address size. So 32 bits is the total address size, which is what we use at the end in order to calculate the tag. So now that we've done that, let's move on. Here's the size of our cache, 120 megabytes. We don't need that just quite yet. Blocks are 4 words, so we have words per block. So in order to calculate our block offset, that's the information we need. So we have 1 block per 4 words. Cool. And each word is 32 bits, which means 1 word, 32 bits or 4 bytes, which I prefer bytes. Leaving everything in bytes simplifies it. Show the fields in a memory address of the cache's 2-way set associative. That's the last piece of info we need. And you'll notice that she likes to use set associative a lot for these questions. And the reason for that is because I'm pretty sure set associative is like the standard memory system. You know, since it's like the best of both worlds kind of thing, the real world likes to use set associative. So this last piece of information means we have per set 2 blocks. 2 blocks per set. So now we have all the information we need. So first things first, we want to draw a little rectangle out, section it off into 4 pieces, and then calculate each position. So starting with the byte offset, which is at this first portion, in order to calculate the byte offset, we need the words to byte ratio. Log base 2 of 4, or how many states do you need in bits? How many bits do you need to represent 4 distinct states? It's going to spit out 2. You need 2 bits to represent 4 in binary. Yeah, in decimal, sorry. So 2 bits to represent 4 states. 4 states, sorry. In order to represent 4 in decimal, you're going to need 3 bits actually. But either way. So 4 states can be represented 0 through 3 with 2 bytes, or 2 bits. So that means log 2 of 4 spits out 2. So we have 2 to start here. And this is the byte offset. Next, we're looking for the block offset. In order to find block offset, we need words per block, which we have right here. Well, a 1 to 4 ratio spits out 2 as well. If you do log 2 of 4 here, it spits out 2 all the same. So we have another 2. Now we need the index, which is where we have to do that big calculation that also involves the total size of the cache. Now, if gigabytes are 2 to the 30th, megabytes are, what's the rule? Megabytes. 2 to the 30th megabyte. 1,000, right? Let's see. Eric, do you remember what a megabyte is? I know we just used it.
The 2 to the 20th, I believe.
Yeah, that makes sense. We'll go with that. All right, if it's 2 to the 20th, that's cool. So we're gonna have to start. So we have all these ratios over here, so I'm just gonna try and work with it this way, where we'd send, say, 128 megabytes times this, times this, times this. So doing this across and, powers of 2, 128 times 2 to the 20th. And then this is going to be, so let's work with 128 to the 20th here. So we have 2 to the 20th, which is going to be minus 4. Well, no, it's going to be minus 2, minus 2, minus 1. So that should be 17 or something. So that's going to be what? 128 times 2 to the 17th power sets. 128 times 2 to the 17th power.
Shouldn't it be 2 to the 15th?
Why? Oh yeah, you're right. It's 5, not it's 5, not 3. Yeah, 2 to the 15th power. Because we have 2, 2, and then we're gonna have 1 bit here, technically, for these ratios. So we have 2 to the 1, 2 to the 2, 2 to the 2, and these are all in the denominator, so they become negative. And then this is 2 to the 20th. So we have 128 times 2 to the 15th, which spits out a big ass number of 4194304. I wonder what happens if I take the log base of that. Log base 2 of that big number spits out 22. And that means the index is 22 bits of our 35 bits total address. So 22. And now we need the tag. So here we're going to do 35, which is our total address size calculated from our main memory. Then we're going to take 22 index bits calculated from this portion, plus our 2 block offset and our 2 byte offset, which gives us 26. 35 minus 26 gives us what? 9. It sounds like 9. 9 tag bits. And there we go. So this would technically be your answer, 92222. And while this could suffice, I would still recommend designating byte block index tag from right to left, so everyone knows what's what. So you'll see that the important information to remember is a gigabyte is 2 to the 30th, a megabyte is 2 to the 20th, and other than that, everything else is a lot more straightforward. So you just need to remember how to do these little ratio tricks, kind of reminds me of chemistry, honestly, some stoichiometry. Either way. So any questions on this one in particular? It's very similar to the last one we did, just with different numbers essentially. And I would not be surprised if the question on the test is literally the exact same one with different numbers once more. No questions? Alrighty. Does anyone want to see another example of these, like the memory dimension thing being done, or would we rather move on to the pipelining? I leave it up to you to decide. How about you, Eric? Which would you rather see? I know there are 2 Erics, but whichever one.
This Eric has no preference.
This Eric has no preference? All right. Well, we haven't done pipelining yet, so I guess we'll do that one instead. We've done this one, and this one has very similar rules. Your task with building memory with 35 bits of address, so there are 2 to 35 data words. Each word consists of so many bits. Parts you have available, you are 18 address bits. So you have a total of 2 to the 18 entries. Each chip outputs 8 bits of data. How many rows required? How many columns required? How many chips required? That such. So after we do the pipelining, I can jump back to this one and very quickly do that if we need to. But let me clear the drawings here. I moved down. Oh, gotta use the mouse. Move down to this. Mouse, mouse, mouse. All right, pipelining. So this is a relatively simple one. So we have 3 instructions. We're assuming a 5-stage pipeline. And it says nothing about forwarding. It doesn't say anything about forwarding, does it? No. Okay. There are dependencies. A source operand cannot be used until it has been written. Okay, so this little line right here tells you we don't have forwarding here. A source operand cannot be used until it has been written as in, stored, written to memory. And that's like the definition of the opposite of forwarding. So we don't have forwarding in this instance. And the question that we're being asked to do, assuming a 5-stage pipeline, how many cycles extra are required to ensure that the correct value of R2 is available for the move instruction in this portion? So let's pick our dependencies. Well, we have no dependencies for R4. Our dependencies are R2 for the load, which takes R4 and shoves it into R2. Move requires R2 to take R2 and shove into R3, and store requires R2 to take R6 and put it into the location pointed to by R2. So depending on the order of operations here, we have dependencies of R2 and only R2. But from what I can tell, I'm pretty sure there's only one like main stall. I think the store will be fine, but it's all about the move, because the instruction or the question is asking how many extra cycles are required to ensure that the correct value of R2 is available for the move instruction, no forwarding. So we have 5 stages here with fetch, operand fetch, execute, memory access, and register write. So let's go through and start. Obviously, the first instruction is always super easy. For simplicity's sake, I'm just going to write one letter for each of these. E, M, M, W. So here's our 5 stages on the first one. Nothing special here. Now, we know the rules here. We can start the next one, pipelining, even with no forwarding. But the thing is, that's supposed to be an F. Either way, the thing is, this says we don't have any forwarding. So we're going to need to take some steps here. So we can extend this. So we have F, 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 and then we can finally start with the operand fetch, the execute, that's supposed to be an E, the execute, the memory, well, that's the memory access, and then we finally get to do our write. And then obviously, once we do operand fetch, we can start the fetch for the next instruction, for the store instruction, which can then do the operand, which can then do the execute, which can then do the memory write, which can then write it completely. And there's a reason as to why we can pull this one off. Because this last line looks like it's forwarding, but it's not, because the store gets special privileges. Either way. So the crux of this question is it's asking how many extra cycles are required. Those extra cycles it's referring to are the amount of times we have to keep fetching the instruction until we finally get to perform the operand once we get R2 from the right. So in this instance, you can see this doesn't count as an extra step because this is required. And then we go to 3, 4, 5. That counts as 3 cycles. Therefore, we burned 3 cycles waiting for that piece of data to come to us. So that's all this question is. So that's basically a free 6 points, honestly. If you get one this simple, be very happy. Now, does anyone want me to explain why that last line looks a little funky? Because you can see that we did an execute. We did an execute immediately after another execute, which looks like forwarding, right? But the thing is, it's not forwarding, because with the store instruction, what you're doing is once this memory address exists in R2, you can shove it there, R6. So it's executed. This memory address now exists. So it's being over here, memory access. Store also is just doing a memory access and a memory write for its execute. So it's allowed to just jump that and immediately begin doing its thing, because this is parallel. These 2 instructions are technically accessing the exact same address. Like R2 has been moved to R3. Whatever's in R2 has been moved to R3, and store is going into R2. So these are technically, R2 and R3 are technically the same at this point. So that's why you're allowed to do this at this last line. So that's that. So that's how to do those. I'll clear those drawings. We'll move back up real quick to just do this one example. And then we'll look at if the stack tracing on this one's a quick one, I'll go over that one as well. So let's look at this. So this has part A, the same one is how many rows, part B, how many columns, and part C is how many chips. These chips being the static RAM chips given some data about the chip. And here's the actual important data about the chip, more data about the chip. So we can start with part A. First piece of information, we have 35 bits of address. So you'll notice, well, actually, that's not important. It gives us the information right there, what I was about to say. Either way, so we have 2 to the 35, which is the first piece of information, which is the dimensions of our words, or the amount of words we have. So now we need to look and see the next thing, 2 to the 18 entries. Entries being words technically, because yes, we've address bits, so entries is the words. Yes, all right, cool. So that means we do 2 to the 35th over to the 18th to start for our part A. And this spits out, what's it gonna spit out, to the 27th? No, that can't be right. To the 17th. Yes, spits out to the 17th. So for part A, the amount of rows we get are 17 rows, or to the 17th rows, sorry. So then for part B, we look to the next pieces of information we're given, which is each word consists of 64 bits, and then the only parts you have available are static RAM chips that have 18 address bits. That's not quite important yet. Here are entries, and each chip outputs 8 bits of data. So that's what's important here. 8 bits of data means that for this chip, its words are 8 bits. So that's the important thing here. So that means for our columns, we are doing 64 divided by 8, which is 8. So we have 2 to the 17th rows. Then we have 8 columns, and then the quantity of chips in all. So the quantity of chips in all, as you remember, comes from multiplying the results of these two simple little calculations. So you do 2 to the 17th times 8, which spits out to the 20th actually. And you can do that little quick calculation because it just so happens that 8 can be written as 2 to the 3rd. So you can just add the, maths, doing maths, quick maths. All right, so that's that. And then this is your answer for part C, part B, part A, right? So that's how that's done. Are there any questions on this one? This type of problem? This one's a lot more, seems a lot more complex because it gives you extra information that you didn't actually need to complete the problem, that being the amount of address and the amount of address in the system that you want to build and the amount of address per RAM chip. You didn't actually need this information. Actually, never mind. Technically, this information is extra because this information is extrapolated to produce this 2 to the 35th and this 2 to the 18th. You see, 18 address bits to the 18th entries, 35 bits of address to the 35th entries. So it's important to understand that those are technically the same piece of information because you could be given a question that doesn't give you 2 to the 35th data words or to the 18 entries. It could instead say it has 35 bits of address and 18 address bits. And that might throw people off because they don't know what to do. But all that means is you just take that number and raise 2 to the power, and that's what you're working with instead. So that's all that means. So I take it there are no questions on that. So I'm going to clear the drawings, mouse over, and roll on down. And look at the stack tracing one and see if it's, this one looks simple, but looks can be deceiving. All right, let's go through and map which commands will affect the stack, right? All right, we start at move. So the first line immediately affects the stack, but this one's looking a little different, right? Remember the first time it was just moving the value 0 into the stack pointer. This time it's moving a hexadecimal address of 0 into the stack pointer. Regardless, it has the same effect of putting the stack pointer at 0. So this affects the stack. We immediately branch to main, which means we jump down here. But as I said, you could do it this way if you wanted to program trace as you were doing this. But it's better, in my opinion. It doesn't matter. We'll do it this way. Why not? All right. So branch to main, jump down to main. Sub SP8. We know what this does. This one's slightly different though, because instead of being at the highest address in the machine, as far as we're aware, it's at the second highest address. So that means we move 2 blocks. So this command right here, the sub SP8, has us going from address 0 to address 7F8, if I'm correct. Yeah, 7F8. All right, let's move on. ADR R6X, that does nothing for us stack-wise. Store R6 stack, that affects the stack. ADR R6Y affects nothing for us. Store R6 SP, that affects the stack. Branch link swap, jump up to swap. Sub SP, that affects the stack pointer, that counts. Load does nothing. Load does nothing. Store in the stack pointer, that counts. Load, wait a second. Yeah, this doesn't affect the stack. Yeah, these don't count. Loads don't count. Loads don't affect the stack. Load doesn't count, load doesn't count. Store affects, this does not affect the stack though, because it's not storing in a stack or a frame pointer. This one, load, doesn't affect the stack 'cause it's a load command. Store isn't affecting the stack either. So we're sitting pretty, nothing's affected the stack this far. This does, because this is incrementing the stack pointer by 4. This counts. Move PCLR. So move PCLR has the same effect as branch link, what is it? BXLR. BXLR and move PCLR do the exact same thing. So remember, if we're moving PCLR and the last branch that we did was, where was it? It was down in main. It was a branch link to swap. That means we go to the next line. Wait, no, branch link to swap. That means we go down here. So we go to add SP8. That affects the stack. Stop. Well, let me do branch stop, and we're done, right? Okay, so this is it. So this one's working out to be a simple one. This looks like we are only doing 8 stack commands. So pray for this on the exam, where you only have to do like 8 boxes, right? Because this is relatively quick. So this one's fast, so I'll do this one real quickly. So yet again, I'll get the solution up and I'll drag it over so we can just explain why it is what it is. That's a lot easier for the stack, and because I can't write very well. Let me open this, open and drag it over. Also turn this off, no more text. There we go. All right, mouse. All right, so this is the same thing. We denoted all of the programs that affected, and looking at it, we have 1, 2, 3, 4, 5, 6, 7, 8 commands. So it doesn't look like we missed anything. So you'll note that in this program, the frame pointer doesn't exist. We never initialized a frame pointer, so we don't have to care about it. If we're not initializing a frame pointer, we can just leave it out and only designate where the stack pointer is at any given time. So as we said last time, the first line, line 0, is a move stack pointer to the 0 address hex. So that does nothing to the stack. It simply moves the SP, the stack pointer, to the address location 0. That's very far away from this little chunk. But then when we go to line 52 from this branch main, which is down here, we immediately sub 8 from the stack pointer, which moves us 1 block to here, moves us another block to here. And now we are at FFFFF8. Hasn't affected any values yet. All it's done is move the stack pointer. Next command is line 60, which is after that sub, which is down here, which is a store command. And activating the store command shoves the contents of R6 into the stack pointer plus 4, which means if you are currently here, you go to the higher address, which is 4 entries higher, and you go right here. And that's where you put it. And that's what happened. Now, the next line, 68, is storing exactly at the stack pointer. So you don't move it, you just shove it where it is currently. This one is subbing from the stack pointer, which causes it to increase 1 box. This one is storing there at the stack pointer's exact location, which shoves 2 in, no problems there. This one's adding, so it's incrementing the stack pointer, which causes it to move down 1 box once more, because it increments it by 4, which counts as 1 box. And our last command is add SP8, which, if you remember, if we're chilling at this position and we add 8, we go up 1 box, which is 4. We need to add another 4, and boom, we jump all the way back, all those addresses back to hex 0. So we're back where we started, which is why it says SP is equal to 0 here. So you can see that this stack tracing problem, which is worth 15 points, could theoretically be done in less than 10 minutes if you really wanted to. You could really grind through this thing, do this whole entire thing in like 5 minutes, 5-10 minutes. So the stack isn't as scary when you know that you have the time you need to do it. You can slow down, you can take your time to trace the program, know what's in the registers at what time, and know what affects the stack. The most important part of stack tracing is taking your time that first look through to make sure you get all of the commands that affect the stack. And the most important thing to look for is note if there's a store command, is it storing into the stack pointer or the frame pointer? And then if it's any other command like a sub or an add or a move, is it affecting the stack or the frame pointer? Those are your important ones. Now there are some edge cases, like in theory, you could have a command that stores the address of the stack pointer into a register, and then you store something into that register later. Now, I don't think she'd do something like that because that's a little rude, because functionally you could have instead of storing, your stack pointer in a register, you could have just put it into the stack pointer instead. But even so, you want to keep track of what the register values. And if the stack pointer or frame pointer are moved into a register at any given time, take special note, because if you do a store command on that register, it will result in you putting data into the stack. And also look for push commands. Push also count as push commands also, directly affect the stack, as we know. So all in all, this is a pretty quick stack tracing problem, which is good. So we'll move on to, I'll move this, I'll get rid of this one. That's the wrong, this is that website. We just did this. We did the stack for this as well, right? Nope, this is a different one, huh? Oh, you'll note in this one, she tells you what affects the stack. I don't know if she'll do that for, I don't know if she'll do that for our final. It'd definitely be nice if she did, but it's not required of her. So it's important to remember how to trace the stack yourself and understand what affects the stack on your own. And it's just going to be a treat if she tells us which commands are directly affecting the stack. That'll just help us out. So we're going to go up here and see if there's anything that's a good review for the other stuff. This is pipelining. Is there forwarding here? The register file cannot do a write. There are data dependencies. Do we have forwarding? The register file, a source operand cannot be used, so this has no forwarding as well. Unfortunate. Let's look at this. Certain memory. This is a cache problem. So let's see which final this is, because this is kind of important to know. This is the December 2019 final. So I'm pretty sure this is the most recent final that she has on file on her website. And in this file, or in this final, you'll note that she doesn't have the questions that we've gone over after those cache questions, which is these ones down here. I hope someone's playing Rust, that are down here, which is, nope, down here, these ones. These, calculate the dimensions of a memory unit that you would have to build. This one's missing those. But the fact that the past two finals have had those questions and that we've gone over it, I'd keep this in mind and make sure that you remember how to do them just in case it shows up. Because losing 6 points on something that's, if you know how to do it, very, very easy, is always kind of annoying. So we were back on this one. This one, right? Yes, this one. So does anyone want to see another, like a third example of, is this better be the December one? Yes, okay. Does anyone want to see an example of the cache or the pipelining again? Or would you rather just do a stack tracing one last time? This one looks like it's going to be a lot of boxes because we have a lot of commands. Any requests? Alrighty. If there are no requests for doing these, I think it's probably better for us to just jump back and do stack tracing instead, because that's probably more important. Because even though this is worth 10 points, as you can see, we've done what 4 gigabytes is. We know that that's 32 bits of address, 32 megabyte cache. We use this to calculate, because this is two-way set associative, we use this to calculate our index later. Blocks are 4 words each, so that means we have 2 bits of block offset, and then each word is 64 bits. So that's a new one. So 64 bits, otherwise known as 8 bytes, means our byte offset is going to be 3 bits instead of 2 bits, as it's been in the last 2 practice problems we've done. So that means so far the running tally here is 5 bits of address. Now, in order to calculate the cache, you're going to do 32 megabytes, which is 32 times 2 to the 20th. No, 2 to the 20th. You do 2 to the 20th minus 2, which is now 2 to the 18th, minus 3, which is now 2 to the 15th. And let's see if we do 32 times 2 to the 15th power. And then we do log base of that, log base 2 of that. We get 20. So it looks like we're working with an index of 20 bits. Fun. So we know that this is 32-bit total, so we do 32 minus 25, that gives us 7. So I just did that without writing anything down, and that is going to give us 7 bits of tag. So you'll note that if you do a lot of these problems and you really understand the underlying concepts, you don't even need to use a pencil. I mean, you'll need to do a calculator at the end for the index calculation because you're going to work with some big numbers. But beyond that, it's pretty simple in general. And then, pipelining like this is, we have no, what is the question here? How many extra cycles are required for the store here, right? And what's for the store instruction? So the dependency across here, we're loading R4 into R2. So R2 is being operated on. So we're going to need this before we can operate in the move. This is going to go into here. And now R6 is being stored. So we remember that the store has special privileges. So I think it's only, it might just straight up be like 0. It might just be 0 extra cycles, depending on the dependencies here. Oh, absolutely not. It is not that, huh? It's a lot of them. We're gonna do this one real quick. This one's useful. So starting off with this is yet again, this is a 5-stage pipeline. So I'm gonna simplify it. I'm gonna do fetch. We're gonna do operate. We're gonna do execute. We're gonna do mem access, and then we're gonna do the write stage. So that's always easy. Now, what's the next step here? Well, we can start with the fetch. Oh, this is a tricky one. I get it. All right. So we then do operand fetch. Now remember, we need to fetch R2, right? We need R2 in order to perform a move because we're copying the contents of R2 into R6. The only way to copy the contents of R2 are to fetch that from memory, right? The problem here is we need to write R2's value into memory first. So we have to delay until we can perform this move instruction until we're past this. So we do another O, and then another O, where we can finally execute, which is cool. And then we can do M and W. Nice. Now we need to store R6 into R2. Now store has special privileges, but you can still see that this is kind of be a little bit of a doozy here because we got to start all the way back here. And then we got to run F. We can finally do an O. But the thing is, in this case, it has excess rules that says a source operand cannot be used until it is written, and the register file cannot do a write and a read at the same register. This line is very important because I'm pretty sure what this line does is it takes away store's special privileges, because in this instance, we have to keep doing operand fetches until the write is complete, where we can then do an execute, and then, oh, that's a bad E, execute a mem and a write here. So in this instance, you'll note that the extra cycles that we have to do is 6. All those repeats. So we start here, fetch, and we're finally actually performing. So this is the 6 extra cycles we perform before we're actually allowed to operate and do the store instruction. So important stuff to note for these questions. If you see this line, the register file cannot do a write to and a read from the same register in a single clock cycle. This will take away store's special privileges, assuming that it's operating on the previous instructions, like assuming it has a dependency between the previous instruction and itself. If it doesn't, then this doesn't matter for it. But in this case, you need to take the contents of R2, move them into R6, and then take the contents of R6 and move them back into R2. This is, now I'm really thinking about it, this instruction is really stupid. But beyond that, because of this instruction being so weird, the dependencies really extend the pipeline process, because you have to wait, and that's because of this little line right here. All right, so that's that. Any questions on this one? This one's kind of a tricky one. Even though it's worth like 6 points, it's still, it's easy enough that if you messed it up, it'd kind of be annoying. No questions on that? All right, coolio. Let's move on and look at the last stack trace. This instance, I don't even have to tell. I don't even have to. If she gives us one like this, I'd be happy because you don't even have to waste time on designating which instructions affect the stack. It just tells you. But because of that, if that's the case, I also anticipate that there's going to be a lot more operations that on the registers, and a lot more stuff being written to the stack over and over again, which is going to probably complicate this thing. Because you see we have, what is this, 24 boxes? Let's count the instructions, 1, 2, 3, 4, 5. Then we go to 9, 10, 11, 12, 13, 14, 15. See, we only have 15 highlighted things, but yeah, that's weird. I don't know why they gave us so many boxes. That feels wrong. Even so, I'll pull up the solution for this. I must have miscounted 16 because that's a lot easier to go over. So let's count exactly 3, 4, 5, and then that goes to 9, 10, 11, 12, 13, 14, 15, right? I counted 15 instructions here. And yet we have 12, 18. So it looks like we did extra stuff. So did she, this is weird. Does she have some things that are operating on the stack but not listed? That can't be right. Oh, wait, never mind. Huh. Oh, this is important to remember, everybody. This is a function we're all familiar with. This is the program that does the cube root of a number, right? This has a lot of loops in it, right? So during stack tracing, even though you have a certain amount of instructions, if you loop through stuff again and register values change, you might perform the same line of code several times, but it'll change the stacks several different ways, right? Let's look for that. Look, 88 occurs twice, 1, 2. 100 occurs here and here, 88 occurs again, 100 occurs again. Yep, that's exactly it. So it's caused by a loop. So this is why being able to program trace just as well as you stack trace is very important. Because if you didn't understand that this was actually looping and that some of these lines are being executed multiple times, you would be very wrong and not be able to perform the stack trace completely correctly. So that's important. So let's look at this. So the first instruction that we are aware of on this is the first line is this move SP. We're all familiar with what this does at this point, which is initialize the stack pointer to the first address, that being 0 in the memory system. So all that does is doesn't affect anything. You just have to list it. The next portion we're also familiar with is subtract 4 from the stack pointer, which if it's at 0, going to -4 is a no-go. So instead you jump to the highest address in the system as far as we're aware, which in this case is 7FC. So SP minus or SP gets its own self subtracted. So there's that. And now we're over here. That's all that's occurred thus far. Unlike the last stack trace that we did, this one has a frame pointer being initialized with the traditional frame pointer initialization process, that being adding the stack pointer, adding 0 to the stack pointer and then saving it into the frame pointer register, which just means you just have a frame pointer and a stack pointer on the same location. Next step, we're doing a store. And we're doing a store of the stack pointer, or well, we're storing the frame pointer into the stack pointer -4. So that means we move the stack pointer up 1 location because -4 moves it up a single box, and we store the frame pointer's memory. Frame pointer, which is currently pointing here, simply store itself right over there, 1 position higher than it currently is in the value of FFFFF8. So now we do another thing, which is add FPSP, which once more, all that does when you do add FPSP, whenever you see this, it just means that you're going to be moving the frame pointer or the stack pointer to the same location. And it really depends the order. If it was add SPFP0, then you'd move the frame pointer to the stack pointer. This one moves the stack pointer to the frame pointer. So you take it from FFFFFC and move it into FFFFF8. So now we do sub SPSP20. 20 divided by 4 is 5. So you shift. Is my mic working? I think my headset just turned off. Can anyone confirm?
Yeah, you're good.
Okay. I don't know why my headset turned off for a second. That was weird. Either way, this just moves up 5 boxes. And all that does is move the stack pointer up 5 boxes. So nothing special there. No changing of the values. Now we do a store. And the frame pointer, which is here, -16. 16 divided by 4 is 4. You move up 1, 2, 3, 4 boxes instead of 5 boxes, and you store a value. But remember, this isn't changing the value of the frame pointer. It's simply using the value of the frame pointer, operating on it here, and then moving data into the address that this points to. But this stays where it is. And then you put the value of R0 in there. Now this is doing a store instruction. Store R3 frame pointer minus 12. Well, we all know 12 divided by 4 is 3. Move up 3 boxes and put the value of R3 into that location. And you know, what's 8 divided by 4? That's 2. You move up 2 boxes, put R3 in here. So we have 410 stored in the -16, -12, -8 slot respectively in reference to the frame pointer's address. Now, last thing here, this is an overwrite because we're going to do store R3 into FP -12. So we move up 3 locations and overwrite the data. So what used to be there, decimal 1 is overwritten with decimal 4. Next line is another store instruction. So we do store R3 FP8. So we move up 2 slots and we overwrite the 0 with the 1. Nothing special there. Store R3 FP12. We're moving up 3 slots and we overwrite the 4 with the 16. As you can see, this equation or this function that was written is basically just doing a bunch of store instructions over and over again with different numbers on the stack. So this doesn't have much difficulty if you are good at program tracing. This type of problem is more program tracing intensive than it is stack tracing intensive, because you're really just, the only thing you're changing is values. And those values, the hard part about those is you need to understand what the program's doing to the registers and the numbers in order to get these new values and then write them to the stack. So it's good that all 3 of these finals have different types of stack tracing problems with different challenges. So let's move on to this portion, which is another store instruction, which overwrote 2 boxes up FFFFF0 with a 2. It was previously a 1. Another store instruction, which moves up 3 slots, -12 divided by 4 moves up 3 slots, overwrites 16 with 64. Another store, move up 2 slots, overwrites 2 with 3. And then down here, we have an add SP FP0. So this is simply, as I said, whenever you see an add with a 0 and an SP and FP, you simply are moving one to the other. So in this case, FP is getting 0 and then being placed into the stack pointer, which means the stack pointer is being moved to the frame pointer. Cool. So it went from FFFFFE4 to FFFFFF8, which is cool. Now here we do load register FP SP4. Now when you do something with an LDR and you do brackets something 4, this is addition. So we go from FFFFFF8 to FFFFFFC. Now the reason this affects both of them and moves them as a cohesive unit is because we're operating on the stack pointer and then moving the frame pointer as well. Should that work that way? Let's think about it. I think she made a mistake here. The previous instruction, we add SPFP0. So that takes the frame pointer's address, which was at FFFFF8, and places it into the stack pointer. Therefore, we move the stack pointer to the frame pointer. Now they're at the same location. The next thing, the LDR FP brackets SP, #4, load register takes a copy. It does not augment the value of what it's operating on. So in this case, if you did load register FP R0, which had contents of 4, and then 4, you would do 4 plus 4 equals 8, and the FP would get 8. But R0 would not be 8. R0 would still be 4. So I think this command here, I think she messed up. I'm pretty sure that the stack pointer would remain here and the frame pointer would move. But I might be wrong. But I think my logic is down there. I think they would separate here. I don't think they're supposed to separate, but they would. Either way. Store R0, FP12. So wherever the frame pointer currently is, you move up 3 boxes and store R0. You can see that we moved up 3 boxes, which happens to be FFFFFF0. And then you store what used to be 3, overwrite it with 64. And then we go down one more line. This isn't actually a stack. This is the last box. We do add SP FP4. So SP equals 0. So this time, yet again, you do the collapsing portion. So it did add FP plus 4. The SP gets moved in the stack and the frame pointer remains. So SP here is what's getting operated on. It's gaining the frame pointer address, which is FFFFFFC plus 4, which sends it to 0. and then it gets put into the stack trace, or it gets put into the stack pointer, meaning the frame pointer gets to stay where it is and the stack pointer, goes off to address 0, and then we're finished. So that's what happens here. We did not do a move SP FP instruction or a load or anything like that. So they stay separate as opposed to both collapsing to the 0, which happened in some of the others. So that's that one. So that's the last final we have. And I think I went over everything. Yeah, this is right. This was right. Right? What is this? What is this? Yeah. This seems wrong. I don't know what she's writing here. 19. 6, 3, 2. What is this? Oh, that's what she did here. She did an intermediate step, but I think that's still similar. Even so, I think that was correct as well. All right, so that's all the finals that I have open for review. Are there any like closing questions that people would like to ask regarding stack tracing or just anything in general, but with primary focus on stack pointer or stack tracing, cache, and pipelining? Any closing statements? Alrighty then. So that kind of wraps up this review session for those 3 topics specifically. As you can see, these finals have other topics in them. We have control signals. This is program tracing. Yeah, risk processing looks pretty easy. Yeah, Francis got said some in the chat. I missed that, but yeah, he's right. We always have this stuff at the beginning. This is all number systems. This is program tracing. So in general, it looks like stack tracing. It looks like stack tracing, cache, and pipelining probably make up 30 to 35% of the test points wise. So it's good to know those things. But just because you've mastered those topics after a bunch of studying doesn't mean you're allowed to slack off on the other topics, particularly writing ARM programs with particular emphasis on ARM programs involving functions. I would really focus on some of that, as well as just general stuff like this stuff seems easy, but you never know. She could hit you with a challenge question version of this, but if you're given one like this, in general, it's relatively simple to do. And something like this, I've seen it so far. We've seen something like this in 3 for 3. So this one showed up 3 times. This program tracing type problem has shown up 3 times. So this is very important to review and understand how this works. You're basically just program tracing without a chart, and you just need to keep track of the iterations you're doing and the values of the registers at any given time. All right. So that's that. Number systems. I hope everyone knows how to do number systems by this point. Otherwise, you're gonna have some problems. I'm sure of it. But and then of course, when it comes to these things, the vocab and such, it's best to go over all of her old final solutions and basically make flashcards or a Quizlet of every single one of the vocab words she uses, because she tends to reuse those questions a lot. It's also good to go back through her annotated slides and look at like the intro to each chapter when she fills in a bunch of vocab words. That's a good place to find more of those potential vocab questions. They're not worth many points, but sometimes 1 point can be the difference between an A and a B or a B and a C, so on and so forth. So it's good to get easy questions correct, so you have a little bit of buffer room to lose points on hard ones. So always plan for where you're going to lose your points. That's what I like to do. All right, so that's that. So I'm going to stop recording and stop the share. Let's stop recording.